let us start. Okay, it will be quite a long class. So let's not waste any more time. Alright, so today we begin chapter 6, which is arithmetic, logic, instructions, and programs. Probably chapter 6 is one of the most important chapters in this course. It is quite a big chapter, and everything over here is actually pretty important. We will begin chapter 6 with the arithmetic instructions, meaning we will deal with addition, subtraction, division, and multiplication. But all of these arithmetic instructions will be carried out only for unsigned numbers. So at the outset of chapter 6, let's see. What do you mean by unsigned numbers? Anyone? What is the meaning of unsigned numbers?
Sir, positive numbers.
Positive numbers. So the name says unsigned, but you used a sign.
Sir, there is no sign bit incorporated.
Okay. There is no sign bit incorporated. Okay. I'm trying to be a little bit more specific. You are right. There is no sign bit incorporated, but what other definition can be given of unsigned numbers from binary number point of view, from binary representation point of view? What can we say?
Sir, positive numbers are basically the direct conversion to binary numbers, but actually negative numbers are not direct conversion to binary numbers. They are converted by the 2's complement. That's why they are kind of different.
Yeah, I take your answer. That is also correct. In a much more simpler language, what else can we say?
Sir, simple conversion of the positive decimal numbers to binary is an unsigned number.
Not that. It can be mixed also. Okay, let me just say, whatever you guys were saying, I mean, most of these things are correct, so there is no problem with that. The definition I was looking for is, in unsigned numbers, when you represent in binary, all the bits in binary represent the number itself. There is no bit which is left to represent the sign of the number. If you consider signed numbers, you know that we leave out the MSB because MSB represents whether the number is positive or negative, and except MSB, rest of the bits represent the number. But in case of unsigned numbers, all the bits in binary represent the number itself. None of the bits are allocated to represent the sign of the number. Is it okay? So we start with the simplest arithmetic instruction, which is addition. All of you already know this. Syntax of addition is add a comma source, and definitely the result will be stored in a. Let us take an example. So from this point onwards, most of the time you will see that the numbers that will be given for arithmetic operations or any type of operations, mostly the numbers will be saved in some particular RAM location or in some memory location. The number will not be given to you straight as constant numbers. So the same thing is happening in example 6.2. You are being said that in RAM memory location starting from 48, there are 7 numbers which are stored. So I'm writing the numbers sequentially. So first of all, we have got 7D, then we got EB in 41H, in 42H we have C5. All the numbers are definitely in hex. Then in 43H we have got 5B. And finally, in 44H, the number stored is 30. So your task is very simple. The task given, not your, the task given is very simple. We need to add all these numbers. So let's start. Let me write the solution, then I will explain. There was another part in the question which said that R7 should contain the high byte of your result and accumulator should contain the low byte of the result. Sorry, I forgot to say this. So in blue color, this is the question. Let's look at the solution now.
Sir, can you raise your voice a bit?
Can't hear. Can you hear now? Is the problem with all of you? Is my voice a bit low? Say something either yes, no, then I can adjust.
Sir, I can hear you, sir.
Sir, a little bit lower compared to previous class.
Low.
Yes, sir.
Okay. Can you hear now the way I'm talking now? Is it okay?
Yes, sir.
Yes, sir.
So let us look at the solution, okay? So now since the numbers are in memory location, if you remember from chapter 5, we need to use one of the addressing modes to fetch the numbers from the memory. What is the name of that addressing mode where we use pointers?
Register indirect addressing.
Exactly, register indirect addressing mode. So that is what we do in the very first line of this code. That is, we move the first address, which is 40H, into R0. And if you remember, we can use only R0 and R1 as pointers. So since you will use R0 as a pointer, we move the first address of the memory location to this pointer. Now, why are we moving 5 to R2? Can anyone say?
Sir, for the loop, for the jump instruction.
Exactly. For controlling the loop. So R2 is your loop control variable. We have got 5 numbers over here, 1, 2, 3, 4, and 5. So that's why you're moving 5 to R2. Then we clear this accumulator and R7 because this is where we will store the result. Then when we execute this for the first time, that is add a comma @R0. So let's start. Initially, the value of R0 is 48. The value of accumulator is 0. So when we execute this line add a @R0, that means A will contain 0 plus whatever is stored in the location held by R0. So R0 holds the address 48. Go to this 48. The number is 70. So 0 and 70 will be added. The result will be 70, which will be stored in the accumulator. So there will be no carry for the first time. Since the accumulator contains 70, there is no carry out. Jump no carry. So this condition is true. So if this condition is true, from here you directly jump to this level because the condition is true. So we do not execute this following line. Rather, we jump to this next level. When we come over here, we increment R0. So now R0 becomes 41H and we decrease R2. So initially R2 was 5. Now we decrease R2. So R2 becomes 4. We can see 4 is still not equal to 0. So we jump to this level again, which is again. Then again we add a @R0. So now if you remember, A already contains 70. With 70, we will add whatever is there in R0. So now R0 contains the address 41H. If I go to 41H, the number is EB. So if I add 7D with EB, what is my result? Can anyone say? How much do you get if you add 7D with EB? Just use your calculator. Come on.
So 168.
168. So now tell me, if your result is 168, what will be stored in the accumulator?
68.
Exactly, 68. So what will happen to the one that is there, the extra one? What will happen to that?
It will carry.
It will move to high R7.
That is later on, but for the time being, it will move to the carry bit of the flag register. So your carry will become 1. So this is how you get your result, that is 168. Now when you come in this line, you see the condition is violated. The condition is not true because there is a carry now. So instead of jumping to the next level, now you come over here. That is, you increment R7. So initially R7 contains 0. Now the value of R7 will be 1. After that, you again increment R0. So now R0 becomes 42H. So we decrease R2. So R2 becomes 3. It is not yet 0. So again we jump in the level again. Again now you are adding over here. So if you add A comma R0, what will be added? Tell me. What are the two numbers that you will add in this particular line now? What are the two numbers that you will add?
So 68 plus C5. I'm not.
68 plus. So it is very simple. A contains 68, so 68 will be there, and R0. So what is the address of R0 now? 42. So go to 42. Look at the number. Definitely 68 plus C5 will be added. So if you add 68 with C5, what is your result?
So 12D.
12D. So what will be there in the accumulator?
So D.
2D. Why only D?
2D, sir. 2D, sir.
Yeah. So carry will again be 1. That means again you will increment your R7. So R7 will become 2. In this way, finally you will see that R7 contains the high byte of your result and accumulator contains the low byte of your result. Is this example understood to all of you? Have you understood this example? Yes, no?
Yes, sir.
Explain from again. Okay, so you understood. So if you have understood, let's move on. Please pay attention, okay? The things that we are covering in chapter 6 are really important. Let us now get introduced with a new instruction, which is add C. So add C simply means add with carry. So it will add both the operands. One of the operand will definitely be your accumulator, because with add we always need the accumulator. The same is true for add C. The destination must always be the accumulator. So when you write add C, both the operands will be added along with the carry. But this one is important only when we add 16 or 32-bit numbers, or the number, any number which is greater than 8-bit. Because on such occasions, if you remember, all of your registers or memory locations are 8-bit sized. That means you can add 2 8-bits at a time. But if the number is 16 or 32-bit, there are other bits of the number that are left out. So there might be a propagation of carry from the lower byte to the higher byte. So in such cases, we need to use add C so that the carry is properly propagated from the lower byte to the higher byte. Things might sound a bit hazy for the time being. So we will take an example, and I believe the example will be clear to all of you. Please pay attention, okay? Time and again I'm saying, try to understand the following example. This one is very important. This is example 6.3 of the book. I don't know whether you have got the exact same example or not, but if the example is not exactly the same, I will suggest you write it. So over here, we will add two 32-bit numbers. I'm giving the numbers, I'm writing the numbers over here. So the numbers that we need to add are 32 bytes, 32-bit sized. All right, these are the two numbers that I need to add. as usual, the numbers will definitely be stored in a memory location because each of the number is 32-bit size. Definitely you cannot store the number in any register. So if I say you that the first number is stored starting from the memory location 48, then what will be there in 48? So I repeat, I'm telling you that the first number over here, the first number is stored in the RAM memory location starting from 48. So what will be the content in the memory location 48? Tell me.
C0.
Exactly. It will be C08. What will be there in 41H?
3B.
Exactly. 3B. So let us write rest of the things. So in 42H, we will have 4, 5. And finally, in 43H, we will have 0, 1, 8. It is needless to say that the first one is your memory location, the second one is the content. I hope you understand at least this much. Now, if I tell you that the second number is stored starting from the memory location 58, then what will be there in 58? What will be there in 58?
FE.
Exactly. There will be FE. I hope the rest of you are also understanding. If there is anyone who is not understanding, you need to raise your voice. Okay, so the numbers are represented. So if we are adding two 32-bit numbers, it is very obvious the result will also be at least 32-bit size. So how will you store the result? Where will you store the result? Tell me how or where? Where will you store the result? Will you store it in register?
Sir, similarly here, like the scratchpad.
Okay, that means you will store in some memory location, isn't it?
Yes, sir.
Let's say the result will be stored starting from the address 68. Let's just assume. So how many memory locations will we need to store the result?
Sir, minimum 4.
Exactly, we will need minimum 4. So let us separate 4 memory locations. Okay. So these are the addresses where our result will be stored. So let's try to differentiate and separate it. Okay. Now tell me, for this particular problem, how many pointers will we need? It is very obvious from the previous example that if the numbers are given from memory location, then we need some pointer, right? So this is also a similar case. So now tell me, how many pointers do we need?
3.
How many?
3.
Okay. So someone say we need 3 pointers. Okay, tell me why you need 3 pointers.
Because 3 different locations.
Exactly. So you are right. So we'll need 1 pointer for the first number. We need another pointer for the second number, and we need a third pointer to store the result. But now the problem is it has been established that we need 3 pointers. This is fine. How many pointers do you have? Which are the registers that can be used as pointer? Tell me that before that.
R0 and
R0 and
R1.
R1.
Exactly. R0 and R1 are the only 2 registers that can be used as pointers. So how many pointers do you have?
2.
Try to think again. Do you have only 2 pointers?
Sir, 8.
Exactly. We have a total of 8 pointers. How? We know that only R0 and R1 can be used as pointers, and we know that there are 4 register banks. In each register bank, there is one R0 and one R1. That means in each register bank, we have got 2 pointers, which makes a total of 4 into 2, 8 pointers. So is it clear that we have a total of 8 pointers?
Yes, sir.
So among those 8 pointers, we will be needing. Any question?
Sir, I didn't understand the 8 pointers factor.
Okay. So we know that we have got 4 register banks, right? Bank 0, bank 1, bank 2, and bank 3. And in each of these register banks, there are 8 registers, right? Starting from R7 all the way to R0. Do you remember this portion?
Yes, sir. Inside RAM.
Exactly, inside RAM. So see, in each register, we have got one R0 and one R1. So these two can also be used as a pointer. These two can also be used as a pointer. Similarly, in bank 2, these two registers can also be used as a pointer, and these two can also be used as a pointer. So how many pointers are you having in total?
8, sir.
8. So you get how we got 8 pointers, right?
Yes, sir.
All right. Now we need only 3 pointers. So how will you manage the 3 pointers? I mean, how will you use, which 3 pointers will you use?
Sir, I think it will be R0 of B1, B2, and B3.
Okay, that also you can do, or you can simply say I will use 2 pointers from B0, 1 pointer from B1, or 2 pointer from B1, 1 pointer from B2. I mean, it is totally up to you. But the main thing is we need pointers from different banks. That means in this code, I mean, throughout the code, we will frequently switch between banks. Did you get this portion, what I just said?
So do you have to use PSW? Yeah.
Of course, we have to use PSW because we will switch between different register banks throughout the code. That's why at the very beginning, before giving you the solution, I tried to explain this portion that we have got 8 pointers, we need 3 pointers. The 3 pointers can be accessed at least by using 2 register banks. So we have to switch between 2 register banks very frequently. Clear up to this? Now let me give you the solution. If you still have a problem, we'll discuss it again. Okay. If you really want to understand this example, I will suggest you sit with a calculator. I will start explaining now. I will go line by line. So if any of you face any problem at any point, you stop me right there. And if you don't understand at any point in the middle, you can stop me right there. But once I finish, please don't say, sir, start from the beginning. Okay? Because it will be difficult for both you and me. So when I will start from the beginning, if at any stage you fail to understand, you can definitely stop me. Okay, let's start. So by default, when we start a code, in which bank are we in? When we start a code by default, in which bank are we in?
Bank 0.
Exactly. By default, at the very beginning, we are in bank 0. So the first line is very obvious. We clear the carry flag, or we clear the carry bit of the PSW register. That means we need the carry, so we are clearing it. So this becomes 0. Okay, so let's write it over here. At the very outset of the program, my carry is 0. Next, we are writing move R2, hashtag 04. So there are two questions. The first question is, this R2 belongs to which bank?
Bank 0.
Bank 0, definitely. So let us write R2 of bank 0 will contain 04H. So the next question is, why 04H? Why not any other value, or what is the significance of this 04?
Because 4 numbers.
Yes.
Exactly. 4 numbers, or we can say 4 byte numbers, right? So we have got 4 byte numbers. So that's why R2 will become the loop control variable. And in each loop, we can add only 1 byte. So in this way, we need to add 4 bytes. That's why the value in R2 is 04. We are done with that. Now move R0, 48. So the same question again. Where does this R0 belong? Bank 0 or bank 1?
0, sir.
Exactly, definitely it is 0. So R0 contains the initial address, which is.
Sir, can you repeat from R2?
Okay. So R2 contains 04, because you see that over here we have got 4 byte numbers, right? 1, 2, 3, 4. And in order to add, we will need this accumulator register. And you know that accumulator register is only 1 byte sized. That means in each loop, you can add only 1 byte of each of these numbers. This one also has 4 bytes. So in one loop, you can add only each byte of these numbers. So if you want to add the entire number, you need to have 4 bytes, or you need to run the loop 4 times. So that's why R2 is my loop control variable, and I am putting 04 because each of the number is 4 byte sized. Is it understood?
Yes, sir.
Okay. Next, R0 belongs to bank 0, we have established, and R0 contains the starting address of the first number. Similarly, R1 is also in bank 0, and R1 contains the starting address of the second number. So R1 contains 58. So we are done explaining up to this. So I hope everyone understood up to this, right? Okay. Now let us move on to the next line. So what is this line doing? Set bit PSW.3. What
We're
is this?
choosing bank 1, sir. Here.
Exactly. Using this line, we are switching to bank 1. How we are doing it, I will not explain it, because this thing has been explained at least 2 or 3 times in the previous classes. So this line, using this line, we are switching to bank 1. Then when we write move R0, this R0 is in which bank?
Bank 1.
Definitely bank 1, because just in the previous line we have switched to bank 1. So when we are in bank 1, we choose R0 and we give the starting address where our result will be stored. So this one now contains 68. Then what is the function of this line? Clear PSW.3.
We are going back to bank 0, sir.
Exactly, we are going back to bank 0. So we are done explaining up to this, and we know that after the last line we are in bank 0. All right. Now when we are over here, move A at the rate R0. So what will be moved in the accumulator? Tell me. What will be moved in the accumulator?
C0.
C0, sir.
Definitely C0. How we understood?
48.
At the rate R0 means we will go to R0. We will go to R0. We will see what is the address held by R0. the address is 48, so we'll go to 48. We will see what is the content of 48 and that will be moved. Very simple. Then we are writing at C accumulator at the rate R1. That means with the accumulator CO will be added with the carry. So what is the value of carry? What is the value of carry in this particular line?
0.
So 0 will be added with at the rate R1. So what will be the other number?
FE.
Exactly. FE. How we found out? We go to R1. We see R1 contains 58. We'll go to the location 58. What is the number? FE. That will be added. So if I add these numbers, what is my result? Tell me what is my result?
So 1BE.
Exactly, 1BE. Okay, this is the result that I get. Therefore, what will be in the accumulator now?
BE.
Right, BE. And where will this one go?
Carry, sir.
Yeah, so now the carry becomes 1. So we are done up to this. Now we will increment R0. Let me remind you, we are still in bank 0. So everything we are doing involves bank 0 only. So we increment R0. So previously the value of R0 was 48. So now it will become 41H. Then we increment R1. Again, R1 was having the value 50H. So this 50H will be gone and the new value will be 51H. Then we are writing set bit PSW3. Once again, what is the function of this line?
Go to bank 1.
Yeah, we are moving to bank 1. So after moving to bank 1, we see this line, move at the rate R0, A. So please explain me what will happen over here.
B
Sir.
will be stored in 60H.
Exactly. So what is happening? Move at the rate R0, A. So we'll go to R0. If you remember, we have just moved to bank 1. We'll go to bank 1. We see R0 contains 60H. We will go to that particular location 60H. And whatever is the content of accumulator will be moved to R0. You can see the content of accumulator is BE. So BE will be moved to 60H. Okay, I'll try to go a bit slow.
Sir, can you repeat this part again? The last part.
Okay, the last part. So I hope you have understood up to this, right?
Yes, sir.
Now, using this line, we again go to bank 1. That means we are switching to bank 1. That means all the registers we call now will be from bank 1. Then we are writing move at the rate R0, accumulator. So the contents of accumulator, you see the content of accumulator is BE. So the content of accumulator will be moved to the address which is held by R0. So we go to R0. If you remember, we are in bank 1. We go to R0. We see the address is 68. So we go to this particular location, memory location 68, and whatever was there in the accumulator, which is BE, will be transferred over here. Have you understood now?
Yes, sir.
Okay. Next, we will increment R0. So now previously R0 was containing 60H. Now R0 will contain 61H. Okay. Then using this line, we are again jumping back to bank 0. Then R2 contains 04. We will decrease R2. So R2 will become 03. R2 will become 03. It is not yet 0. So again, we will jump to this level, which is back. All right. Now we are in back. Again, we find the instruction move A at the rate R0. That means whatever A content will be overwritten. It doesn't matter what A is containing. So it will be overwritten. And now what will be there in accumulator?
The 3B.
Exactly. Now over here we will find 3B. Why? You see, we are moving the content of the address held by R0 of bank 0. So in bank 0, we go to R0. We see the address is 41. We go to this 41. we see the number is 3b. So 3b will be moved over here. Then we are writing add carry a comma at the rate r1. That means with 3b, my carry will be added. What is the value of carry?
1.
1. With this, the content of the address held by R1 will be added. So what will be the other number?
058.
Definitely, very simple. See, R1. So you go to R1, you see the value of R1 is 51. You go to 51, the number is 05. So 05 will be added. So if I add these three numbers, what is my result?
41.
41H. That means my accumulator will contain 41H, and what will be the value in the carry?
0.
Exactly, it will become 0. So in the same way, in this particular memory location, like previous one, 41H will be stored. If you keep going, you will see that 62 will contain 0CH, and finally 63 will contain 58H. Thus, after adding these two numbers, this is the result that you get, which is stored in this particular memory location. Okay. So if any one of you have any question, you can ask.
Sir, what if there is more than what is the
Yeah, I got your
summation
question.
becomes
I got
more
your
than
question. Yeah, I got your question. Okay. So that was the question I was expecting. So before answering that question, those who did not understand those who did not understood the question doesn't matter. Just try to focus. Okay. Assume a 1 byte number. What is the largest 1 byte number that you can imagine? Tell me. The largest 1 byte number. What is the largest 1 byte number?
F.
Hatta if na, 1 byte. Okay, 1 byte means 8 bits. Okay, so these are the largest 1 byte number that we can have. So if we add these two, what is my result?
1 FE.
1 FE. Okay, what I'm trying to say is, if your operand is 1 byte size, and if you are allocating 2 bytes for the result, then in the first byte of the result, you can have a maximum of 0, 0, sorry. 1. Yeah, the maximum result that you can have in the higher byte is 0001. Have you understood this portion?
yes, sir.
Okay. If you have understood this portion, now let me give you the solution. What will happen? So the question was, what will happen if there is a carry when you are adding the last two bytes? I mean, when you are adding 01 and 56 for the last time, what if the numbers are such that at the end there is another carry? So what will happen at that time? That was your question, isn't it?
Yes, sir.
Okay. If that is the question, tell me, if we get a carry at the last, where are we supposed to store the carry? Where are we?
Register.
We are storing the result over here.
Sir,
So
we
where-
can store it in 64.
Exactly. So you will maintain the symmetry, isn't it? So 64H should contain 01 hex, right? I mean, that is the maximum it can have. You cannot have any other number other than 01. Do you understand this portion at least?
Yes, sir.
Okay. So that means we need to add simple 2 or 3 lines. So what are the lines? Let's make it general. If there is no bit, if there is no carry, then we'll jump to a label. Say the name of the label is log. You can give any name, okay? Doesn't matter. So if there is no carry, we'll go to log. We will end the program. Nothing. But if there is a carry, then what we need to do? Try to recall we are in bank 0 of this line. So we need to switch back to bank 1. So we will write set bit PSW.3. So we move to bank 1. Try to remember from this line, after you have incremented R0 of bank 1, you have not used it. That means after this line, you are in the 64H location. So you don't need to increment. You can simply write move @R0, 01 hex, and that will give you your solution. Have you understood?
Yes, sir.
So, I mean, there are a lot of ways by which you can do it, definitely. There are other ways, but this is one of the way. So now this is the complete set of code. Even if your answer is more than 32 bits, and if you write this code, then you will be able to accommodate the entire result in this memory location. Clear to all of you? Any question? Come on, if there is someone who wants me to start from the beginning, I can still do that, okay? So if there is someone, you can say. Again, I'm requesting you time and again, please understand these examples, okay? Remember, the situation will be reversed. That means you will also have to come to me to request. So don't make sure that you are requesting. So understand now. I hope you understood. So let's move on. All right, next we discuss BCD number system, which is binary coded decimal. So the binary representation of these 10 digits, that is from 0 to 9, and that is in the decimal number system, whatever we have, these 10 digits. So the binary representation of these 10 digits is called BCD. So the representation is very simple. You already know, if your digits are from 0 up to 9, and these are the corresponding BCD representation. Now there can be two types of BCD. One is unpacked BCD and another is packed BCD. So the definition itself is self-explanatory. Still, I'm giving an example. Like if you want to store, say 9 in unpacked BCD, it will be stored like this. This is 9, which is stored in unpacked BCD. But you see, in packed BCD, a single byte will have two BCD numbers. So if we want to store 3 and 9, then it will be stored like this: 0011 and then 1001. So this will give you 3 in BCD, and the later one will give you 9 in BCD. So this is how your BCD numbers are stored, either in unpacked format or in packed format. Anything else you want me to explain over here?
Sir,
Yes.
unpacked takes 8 bits of space for a single number.
Your all the registers or memory locations all are 8 bits, right? So you cannot allocate 4 bits for anything. So that's why this format is given. You have to utilize all the 8 bits. When we go in unpacked, we actually waste the higher neighbor because we are keeping it 0. So packed BCD is from the point of view of memory allocation, this one is better because you are having, you are utilizing all the bits. All right.
Yes, sir.
Sir.
Hmm.
Sir, so are we saving the 39 decimal number in this format?
39. Yeah. This is not 39. This is 3 and 9. So how you will access it totally depends on the programmer. See, when you are giving this binary, your MUSI doesn't know whether this is BCD or hex or what. Your MUSI does not know. So it totally depends on the programmer how he exploits this number. Got my point?
Yes, sir.
Now let us see a problem which is associated with this BCD numbering system. Okay, let us see what is the problem we have. Say we are trying to add two BCD numbers. The numbers are 17 and 28. Now, as you know, your MUSI does not understand BCD. Okay, it simply doesn't understand. So whatever you give, it will be in hex. So definitely you need to give two numbers as hex as well. So if you give these numbers as hex and if you add 17h plus 28, what will be your result? What will be your result?
3F.
Yeah, so the result will be 3F. But the programmer intended that these numbers are BCD. So if we add in BCD number system, what is the result that we expect?
So 45.
Right. We expect the result 45. So how can we go from 3F to 45? What can we do to go from 3F to 45?
No idea, sir.
No idea. Okay.
So add 6.
Exactly. That is what I was asking. So we will add 6. So if you add 6, you will end up getting 45x. So this is the result that we are expecting, but this is the result that we got. So the problem is when we intend BCD addition, these are the type of the result that we expect, but we get this type of result. So if we add 6, we get the expected result. This does not mean every time adding 6 will give you your desired result. So let us see another example. So there are another BCD numbers which are trying to add, which are 52 and 87. So if you add these two in hex, what is the result?
Nine C. Sorry. Yes, sir. C9.
Sir, D9.
Sir, D9.
Yeah. D9x. And what is the result that we expect? এটা যোগ করতে তো ক্যালকুলেটর লাগে না, তো মুখোমুখি হয়।
Sir, 139. Sir.
Yeah. So now tell me, how can we go to 139 from D9H?
Sir, it's already in that format, sir.
Which format?
So D means 13, sir. I don't know what to say about this.
Is D a BCD number?
60, sir.
Yeah. So we need to add another 60. So if you add 60, the result you get is 139. And definitely it will be hex. So forget about the hex, is the result that we get. Okay, so the problem you see is your numbers will always be added in hex. Okay, so sometimes you need to add 6 with the lower bit, or you need to add 6 with the higher bit. In other way, sometimes we need to add 6, sometimes we need to add 60. So this is the problem, and the solution is this, that either adding 6 or adding 60. So did you understand the problem and the solution? It is not yet over, but at least did you understand what we are dealing with over here? Yes, no, sir, explain again. Come on. Any type of question you should ask. Okay, so I hope you understood. So the problem was we were getting a separate answer, and the solution is adding either 6 or 60. So there is a separate instruction in MuC, which is DA. So this instruction solves the problem associated with this type of things. So let us see now what DA does. The DA instruction, whatever I have written, I don't think I need to explain any of these things. Now I will write DA working logic, and I will expect that you will go through this logic, and based on this logic, I will ask a question. Definitely, I expect that you be able to answer. So look at the working logic, okay, and try to understand on your own.
Sir, we can see what you have written in the bottom.
Is that so? What is the last thing that you can read?
So CY is equal to 1, add, then the last part is cut. Oh, sorry, sir. It's my.
Can you see?
You need to remove the cursor from the screen. Then it
Yes,
will-
sir, I can see now. It's my monitor.
This one is not yet over. The red mark portion is not yet over. So assume this is the instruction given. Move A 29H, add A 18H, and then DAA. So let us see whether DA satisfies the conditions or not. So DA means decimal adjust for addition, which is fine. DA works only on A. So we have got A operand with DA. So this condition is satisfied. DA must be used after addition of BCD operands. We can see both the operands are BCD. So we can use DA now. And DA works only after add instruction. So right after add instruction, we have used DA. So everything is okay. Now this is the working logic. And I have break down the problem over here. Now tell me which logic will you apply and what will you do over here? Tell me. I hope you got the question, what I'm trying to ask. This is your DA working logic. So tell me what will happen.
So we'll use the first logics.
You will use the first logic. Is that what you say?
Yes, sir.
Okay. Why? You need to explain.
Sir, because the lower nibble is greater than 9, sir. So we use the second portion.
The lower nibble is greater than 9. I mean, is it true?
Sir, the second part is true, sir. The AC is equal to 1.
So AC is equal to 1. Okay. How is AC equal to 1?
Sir, auxiliary carry, sir. AC is auxiliary carry, maybe, sir. And 9 plus 8 is equal to, sir.
You are thinking over here. If you use auxiliary carry, you need to move over here.
Sir, in the BCD, sir, in the half part, 1 plus 1 is becomes 0. So there's an auxiliary carry here. So we have to use the first logic.
When does auxiliary carry become 1? Tell me that.
So when there is a carry from the fourth to the fifth bit.
Yes, sir.
Don't say fourth, fifth bit. Come on. By this time, at least what you said is correct. Okay. But how do you start counting? We say that when there is a carry from D3 to D4, is it not how we say?
Yes, sir.
So if there is a carry from D3 to D4, in that case, my auxiliary carry becomes 1. So you see that is true. So when you are going from here to here, this is your D3, this is your D4. When you are going from here to here, there is a carry. So if this condition is satisfied, we will add 0, 1, 1, 0, where? In the upper nibble or in the lower nibble? Where will we
Lower.
add? Definitely
And the lower nibble, sir.
Lower nibble. So we add 0, 1, 1, 0. And now the result becomes 1, 1, 1, 0, and 0, 0, 1, 0. So if you convert it, this is the same as adding 6. So the result you get is 47. So this is how this is how you need to apply the logic, and this is how your DA works. Clear to all of you? Any question over here? You might have some questions. Come on, you need to ask. Fine, if you don't ask, that is totally up to you.
Sir, what if we have both? Sir, what if we have both auxiliary carry and carry flag at the end of it?
That's what I was expecting. This will not be the case. You will not have auxiliary carry and carry is equal to 1. This will not happen in BCD. You can try to think of some numbers. try some combinations, but both of these conditions will not be true at the same time. Is it okay?
Yes, sir.
Any other question?
Sir, the instruction DAA, is it fulfilled? It only has one operand here.
Yeah, it has only one operand, one and only one. You cannot use any other. Look at this line. DA works only on A. Okay, so you have only one operand.
So if we add 99 plus 99, then what will happen?
Let's see. So go to hex. We add. Okay, let's take this example. So we are adding 99 hex with 99 hex. If we add, what is the result? 132 hex. And what is the result that we expect? What is the result that you expect?
198.
198. So let us see the binary form of 99, right? So 99 gives you no. What is the BCD of 99? Tell me. What is the BCD of 9?
Sir, 1001.
1001, and this will be 1001. So this will also be 1001. This will be 1001. Good example. Let's see. So does it satisfy both? So let's add 1 plus 1 is 0. 1 will be there. 1 plus 1 is again 0. So 1 is carried. 1 plus 1 is 0. Plus 1 makes it 1. It will be 1, 0. Is it okay? Is it what we get? Is the addition okay?
Yes, sir.
Yes, sir.
Just a second. Yeah, the addition is okay. So what happens over here is your auxiliary carry becomes 1, right?
Yes, sir.
Carry is also 1.
Yes, sir.
Right? Then is this number greater than 9? No. This number is greater than 9? No. Good question. So tell me, by the previous logic, what is supposed to happen? See the previous logic, what is supposed to happen?
Sir, add 6 to the upper nibble, sir.
What about the lower nibble? Your auxiliary carry is 1. So why
Sir,
not 1?
also adding to the lower nibble.
So I take back my answer where I said both the conditions will not be true. So you will add this 6 to both upper and lower nibbles because both the conditions are being true. So you add 0, 1, 1, 0 and 0, 1, 1, 0. So if you add both, your result will be 1 plus 1 is 0, 1 plus 1 is 0 and 1. Again 1, 1 plus 1 is 0, 1 plus 1 is 0 and 1. Forget about this carry. So it will be equivalent to adding 66 hex and you will end up getting 198. So I take back my answer, okay? I did not know that this might happen. So if you get both the conditions true, then you will apply both the conditions. That means you will add 66. Is it okay? Is it understood?
Yes.
Whoever raised this question, thank you very much. And please discuss it with the other two sections, please personally. I told them that these two cannot be true at the same time, but you gave me the example and this can be true. So if this is true, this is what we need to do. So please share it with the other two sections, must. Okay, any other question over here? If no, then let us see an example. This is example 6.4 of the book. I might take 5 minutes extra, okay? So please bear with me. So this is an example of BCD number addition. You are given 5 BCD numbers in the memory location starting from 48. The numbers are given over here. Okay, these are the 5 BCD numbers. The task is very simple. We need to add all these BCD numbers. So I'm giving you the solution. I don't think I will explain the code, but I will ask you something. Look at the code and tell me in which registers are your results stored. Look at the code and tell me in which registers are your results stored.
Sir, R7.
Only one register?
And
And
sir, maybe only one register, sir. I'm seeing it.
how can you save your result in just one register? All of the numbers are byte size, so definitely you will need 2 bytes. Look at the code and try to
Sir,
say. Exactly. Your result is stored in accumulator and R7. So tell me which one contains higher byte and which one contains the lower byte?
Sir, accumulator lower byte, sir. R7 higher byte.
Accumulator contains the lower byte and R7 contains the higher byte. I mean, by this stage, you should be able to answer these things much faster, okay? It's okay, maybe you have not prepared or something like that. It's okay, but this is what. Anyway, I will not explain the code, and up to this is your made syllabus. This is your last class before made. We will have another class on Thursday where I will discuss only about your mid semester. I mean, how many questions will be there, what will be the full marks, what will be the timing, how you have to answer, whether there will be options or not, what you have to do, the do's and don'ts, all these things I will discuss on that class. So apart from your mid questions and all, if you have any question regarding this topic or regarding whatever you have learned so far, you can ask now. Okay, before that, let me just take your attendance because the time is already up. And after that, those who will have your questions, you might stay back.